All right, quick review of the sort of stuff you will need. All right, so the definition of work. A, Z. It means capacity to do work. And whenever you do work, you transfer energy, right? So work is a process of transferring energy. So energy means capacity to do work. And then when you do work, you process energy. So it's a process of transferring energy. Work is something that happens when there's force causing displacement. So there's going to be force, applied force. And applied force is going to be somehow influencing the motion. It could be responsible for the motion, or it could be opposing the motion. So the work is something that happens when there's force and displacement. That's what it means. It's a combination of force and displacement. All right, so summary statement is based upon that. So that if there's force causing displacement, the work is being done. When you're doing work, displacement could take place along the X direction, Y direction, or Z direction. Some books will say D, some books will say S. All right, so the standard notations are the ones that we're using. R is it's a space holder for X, Y, Z that you got. So the work is going to be a combination of force and displacement. So force could be influencing the motion. It could be in the same direction as displacement, obviously. So which means that it's going to be adding on to motion. It could be in the opposite direction of displacement, which means that it could be taken away from motion. So it can be adding on to motion. It could be taken away. It could be taking away from motion, in the sense that it could add energy to the system, or it could take energy away from the system. That's what it means. All right. So the work is a process of transferring energy. So if it's in the direction of motion, it's going to increase the energy. If it's in the opposite direction of motion, if it's opposing motion, it'll take energy away from the system. Proper unit is joules. In the United States, we use kilocalories. We call it a calorie. So it's a United States calorie, 1,000 calories in physics. And so that's it. So the entire definition of work is contained within this box. All right. So work is something that happens when there's a combination of force and displacement. And it's a process of transferring energy. When force is along the direction of displacement, it's going to add on to motion. If it's opposing motion, obviously it's going to take away from motion. So it can add energy to the system, or it can take energy away from the system. So that's in essence what it means. All right, so the force can be coming at an angle. If it's coming at an angle, the component of the force that's going to be responsible for transferring energy is the component which is parallel to the motion itself. All right, so the parallel component of force is going to be the cosine of the angle of the actual force that you're looking at. So for work to happen, the force needs to have a component along the direction of motion. All right, so we got the background. All right, so displacement as well as the force, those are vectors, which means that they got direction as well as magnitude. So when the force and displacement are in the same direction, so force is going to be positive, displacement is positive. So the energy is going to be positive, right? Positive work is being done, which means that the energy is being transferred. So the energy is increasing under the circumstances. So that's what it means. When the force is opposing motion, force is negative, displacement is positive. Negative times positive is going to be negative. Negative work means energy is being lost, which means that the energy is taken away. So here, there's a positive gain, positive increase. So positive work is going to have a positive effect on energy, which means that the energy is going to go up. Negative work is going to have a negative effect on energy, which means that the energy is going to go down. All right, so the third one is force is in the opposite direction, motion is in the horizontal direction. So this force does not have a component on the direction of motion. So which means that no work is being done. No energy is being transferred. So summary statement is if the force is along the direction of motion, work is positive, energy is gained. Force is opposing motion, work is negative, energy is lost. Force doesn't have a component along the direction of motion, no work is being done. All right, so this formula is a summary statement for everything that we discussed so far. All right, so if the angle is 0 between the force and the displacement, which means that the force is along the direction of displacement. So cosine of 0 is going to be 1. So as a result, this expression is going to be 1. So it's going to give you positive work. So the energy is going to be gained. So this is the case that we're looking at. If the force is at 180 degrees to motion, which means that it's going to be in the opposite direction of motion, cosine of 180 degrees is going to be -1. So which means that this expression is going to be negative. So which means that the change in energy is going to be negative, which means that the energy is going down. So which means that the energy is being lost. If the angle is 90 degrees, cosine of 90 is going to be 0. And then boom, so this one is going to be 0. So the amount of work done is going to be 0. So there's no energy is being transferred. Those circumstances. Actually, more force and displacement, if they're in the same direction, work is positive, so the energy. So whatever it is that you're lifting is going to become lifting. The weights will become energized. And then when you pull them down, you end up taking the energy away from the weights.
You know what they say, no pain, no brain.
Okay, so this is positive work. Force and displacement, they were in the same direction. So the energy transferred to the weights. All right, so what that means is these weights are energized. If you're not careful with them, they got capacity to do work on it. What that means is they can apply a force on you and they can displace you in the direction of the force. So which means that the energy gets transferred back to you.
Remember, it's lift with your legs, collapse with your spine.
Positive work. Force and displacement. We're in the same direction. So energy got transferred. Energy got transferred to the weights. So which means that these weights right now got energy. Once again, it's the same thing, which means that if you're not careful, they can do work on you. They got the capacity to do work. What that means is they got the capacity to apply a force on you and make you move along the direction of the force. All right, both these guys kind of have the same technique. I wonder if they got the same trainer. Displacement is in the forward direction. The force is in the opposite direction. This force does not have a component along the direction of motion. So no work is being done. Now, this statement requires a qualification. The qualification is that this person has to be moving in a straight line at a constant speed, which means that there has to be no acceleration along this direction, implying that the net force along this direction is zero. If that's the case, this force is not responsible for that displacement. So which means that no work is being done. There's force, no displacement. Pushing up against the wall is not moving, no work is being done. No energy is being transferred. There's force, there's displacement. All right, so the work is being done. The ball is speeding up. So the energy is going to be transferred in the form of kinetic energy. All right, so kinetic energy is the energy of motion. It's going to be related to speed. Formula is 1/2 mv squared. All right, so kinetic energy is related to speed, square of the speed. For a given mass, it depends on the square of the speed. Potential energy is the stored energy by the amount of work that you do against the conservative force, like gravity, by lifting something up. So force causing displacement. This is the amount of work being done. You transfer energy to the object. So this is the amount of energy transferred to the object. So it's going to depend on, for a given mass, it depends on the height. For a given height, it depends on the mass. For a given height, it depends on the weight. Heavier objects at the same height will have more potential energy. More massive objects at the same height will have more potential energy. And for a given mass, it depends on the height. For the same mass, higher up you go, the larger the potential energy is. All right, so those are the interpretations. So potential energy represents the stored energy. You store energy in an object by doing work against a conservative force. So the question is, what is a conservative force? All right, so potential energy, the gravitational potential energy, is the amount of energy stored in an object by virtue of displacing this object against gravity in the opposite direction. So it's going to be related to height. Combination of kinetic and potential energy is known as mechanical energy. And mechanical energy will be constant or conserved if there's a conservative force acting. So once you let something go, like a ball, when you let it go, if gravity is a conservative force, for example, the motion is going to be under the influence of gravity, for example. If the gravity is a conservative force, what happens is the mechanical energy remains constant. So when you drop a ball, its potential energy is going to go down because of the height. The vertical distance is going down. And then its kinetic energy is going to go up because it's speeding up. All right, so which means that that potential energy will get converted into kinetic energy, provided that the mechanical energy is constant. So that's what it means. When you throw a ball in the opposite direction against gravity, it's going to start to slow down as it's getting height, right? So its kinetic energy gets converted into potential energy as its mechanical energy remains constant. All right, so this is known as the conservation of mechanical energy. Mechanical energy is constant, will remain constant, provided that the force responsible for the motion is a conservative force. So any force that conserves mechanical energy is known as a conservative force. Prime example of a conservative force is gravity. The second one is the restoring force. All right, so the restoring force is something that we discussed before, so that's going to require a little bit of a review as well, especially for university physics students. College physics students, it's not that important, but university physics students, you will need to know. So conservation of mechanical energy is the constancy of mechanical energy. And the mechanical energy will be constant only if the force responsible for that motion is a conservative force, like gravity.
Did you ever wonder how they figure out the altitude of a mountain? Well, two guys climb to the top, they each take the end of a tape measure, and then they flip a coin.
All right, so relative to the base of the mountain, both of them got potential energy, right? So what happens if you lose your balance? Gravity takes over. It's a conservative force. What does it do? It's going to conserve mechanical energy. So it's going to take your potential energy, and then it's going to start to convert it into kinetic energy. You're going to go faster. I like this guy. He did not flinch a muscle. Very smart. He knows that there's nothing he could do. And then he's got two options: either worry about the guy or enjoy the scenery. I think he decided to focus on the positive one. That guy's a gunner.
After 12 years of intense testing, self-proclaimed grizzly bear expert Troy Hurtubise built his most advanced grizzly-proof suit yet.
You can shut this now.
This may be the design that finally enables Troy to safely enter a sleeping grizzly's den to study the animal.
That's what I want. Go ahead.
The Ursus Mark VI is one of a kind. Titanium gives it strength. Chainmail provides protection. Inflatable airbags that act as shock absorbers line the inside.
By the time I got to the Ursus Mark VI, I was able to withstand 4,000 pounds per square inch and eliminate the danger from claws and teeth if the experimentation went awry.
Good enough of that?
Troy tests the Mark VI's outer shell against a 12-gauge shotgun slug capable of dropping a moose. If the balloon inside pops, Troy will know that the suit cannot withstand the force of the slug.
Close her up. That's it.
The slug embeds itself in the soft rubber skin, but doesn't pierce the titanium armor.
There you go. There's the balloon right there. Did not break at all. Fantastic.
So it's fine? It's perfect. It's perfect. It's perfect, yeah.
Troy sees no reason not to enter a grizzly's den,
Along with 300 pounds.
since he's confident his suit will protect him,
I'm good. I'm good.
and he's designed one final test to prove it.
Want to go? Yeah, you sure?
According to Troy, this experiment is far more dangerous than any so far because it best simulates the power of a grizzly's attack.
It's not the claws and teeth I'm worried about with the suit. I've got chainmail. It's the power. It'll break the back of a cow in one shot.
To mirror that power, Troy must do more than equal its force. By replicating the size of a grizzly's paw, he creates the same PSI, or pounds per square inch of force.
Grizzly's paw is 9 inches in diameter. That's what you're looking at on this brick.
The cement block is checked and rechecked to make sure it strikes Troy directly in the chest.
You're standing up straight there?
Yeah, stand up straight.
The plan is to gradually increase the force of the block in small increments, beginning with a virtually harmless distance of 5 feet.
That's the mark.
The helmet is bolted in place.
You guys tell me when so I can stand up straight.
Troy expects a small impact,
A little bit now.
but something goes wrong, and the cement block is accidentally raised to a height of 30 feet, at least.
far? All right? How you feeling there, Troy?
The concentrated force strikes Troy smack in the chest. The suit seems to survive the impact.
Just a little bit now.
A camera on Troy's helmet reveals his limited visibility, causing Troy to believe the cement block hit him from only 5 feet away.
Too low, knocked the wind out of me.
Oh, did it?
Yeah.
I see the hit you right
Hit
there.
me right in the chest, well, knocked the wind out of me.
Yeah.
How high was that? Show me again. Hold it. Don't let it go either. Show me how high it was.
I went all the way. All the way to the top.
You went all the way to the top on that hit?
Yeah.
We were supposed to go 5 feet, 10 feet. You ran into the top? Oh, I love it. Full parameters.
Despite the mishap, Troy is thrilled with the outcome.
I honestly didn't believe the Mark VI could handle it.
Okay, so what was the speed of the block at the bottom of the pendulum? So that's the sort of stuff that we will need to focus on for the task mathematically. But before we do that, let's just do a fast review of the concept. So the energy is the capacity to do work. And whenever you do work, you transfer energy. And the work is a combination of force and displacement. Work is positive when force and displacement are in the same direction. It's going to be negative when the force is opposite motion. No work means number of things. Either the force is 90 degrees to motion, or there's force, there's no motion. There's motion, but there's absolutely no force. The unit for work and the unit for energy will be the same. It's going to be joules in physics, calories in the United States. So the conversion factor is there if you want to do the conversion. So positive work occurs whenever the force and displacement are in the same direction, like pushing on a table, provided that it moves in the direction of the push or pull. Negative work is slightly more complicated. So there has to be a force opposing motion. I think a fast moving car coming to a stop due to skidding is an example. So motion is in the forward direction and the frictional force is opposing motion. All right, so we discussed no work, we discussed positive work, we discussed negative work. All right, so no work is this one, positive work, force and displacement in the same direction. Negative work, force is opposing motion. So when the work is positive, the energy is gained. When the force is When the work is negative, the energy is lost. When there's no work, no energy is being transferred. Lifting a book, the work is positive. Force and displacement are in the same direction. All right, so putting a book down on a table, the work is negative because force and displacement are in opposite directions. Carrying a book, no work because the force is 90 degrees to motion, so it does not contribute to motion. Fast moving car skating to stop due to friction. Work is negative because the force is opposed to motion. Energy is being lost. The amount of work done on the moon by gravity is 0 because the force is 90 degrees to motion. So which means that no work is being done. And that's it. So potential energy is for a given mass depends on the height. That's the stored energy by the amount of work that you did against gravity by lifting something up. Kinetic energy for a given mass depends on the speed. Mechanical energy is a combination of kinetic and potential energies. Meaning of the conservation of mechanical energy means the constancy of mechanical energy. When you drop a ball, its kinetic energy is going to go up because it's speeding up. When you drop a ball, its potential energy goes down because height is going down, decreasing. And when you drop a ball, its mechanical energy will remain constant because of gravity. It happens to be a conservative force. And that's pretty much it for that one. All right, so conservative force conserves mechanical energy. All right, so in Galileo's incline experiment, the ball is going to go back up to the same height because gravity is a conservative force. That's what it is. So it converts potential energy into kinetic back into potential energy. That's it. So conservative forces will conserve mechanical energy. And gravity is a conservative force. If you have a propulsive force, for example, it's not a conservative force. Propulsive force is going to let you gain mechanical energy. So the propulsive force is going to let you gain mechanical energy. So mechanical energy of the system is going to go up. So the mechanical energy is gained in the system. So the question is, where does the extra mechanical energy come from? Well, extra energy is going to come from a conversion process. All right, so if it's a motorcycle, if it's a car, if you're using your muscles, so chemical energy gets converted into mechanical energy, for example. All right, so you got light, you got heat, you got nuclear energy. So one of these energies will get converted into mechanical energy. So there's a conversion that takes place. So you're not creating energy, you're just converting energy from one form to another, in essence. So propulsive force is not a conservative force. Because of propulsive force, you end up gaining mechanical energy, and the energy gained is going to come from some other form of energy. So it gets converted from some other forms of energy. All right, well, if there's friction present, all right, so you will lose mechanical energy. The amount of energy lost is not destroyed. What happens is through friction, the amount of mechanical energy which is lost is going to appear in the form of sound, heat, light. If there's too much friction, it can turn into fire, for example, and then it'll turn into deformation. So even if the mechanical energy is not conserved, what do we know? The total energy is still conserved, right? All right, so this is known as the conservation of total energy. Energy cannot be destroyed or created. It can only be converted from one form to another.
It's a slam dunk contest in Miami, and reporter Russell Shimoka thinks he's got...
All right, so this guy has a lot of potential energy. It's got a lot of potential. Every single living thing is going to have potential energy stored in it, which means that it's got energy stored in him in the form of chemical energy, in essence. And now what happens to that chemical energy? It turns into heat, guys. All right, so whatever it is that you eat, got chemical energy in it. And obviously there's a process that takes place. The food gets processed. It turns into calories, meaning that it's going to turn into heat. And then the muscles end up using them, so it turns into mechanical energy.
The right stuff.
All right, so he's just running, so he takes his potential energy and turns into mechanical energy.
It's a slam dunk contest in Miami, and reporter Russell Shimoka thinks he's got the right stuff.
All right, now we're in the territory of a conservative force, jump. Now everything's going to be under the influence of gravity. All right, so what does gravity do? Gravity is going to take its potential energy, turn it into kinetic energy. And then there was a mat down there, trampoline. So he stretched the surface. There was a restoring force. So he stored energy in the mat, and the restoring force took the energy, the potential energy, and gave it back to him. So that energy turns into kinetic energy. Now he's rising up. Gravity is influencing the motion. So gravity is going to take his kinetic energy and turn it into potential energy. And then now he's got potential energy. He's trying to hold on to it at this point. And then as soon as he lets go, once again, gravity is going to take his potential energy. It's going to turn into kinetic energy. On impact, he's got kinetic energy, right? So what happens to that kinetic energy on impact? So the kinetic energy dissipated, which means that it turned into something else. It turned into sound. You guys heard the thump. And then, obviously, the body's going to heat up. There's going to be a deformation.
Once again, in slow motion, you can see Russell's face bounce right off the floor. He fractures his cheekbone.
All right, so the final form was deformation, so his cheekbone got fractured.
But he's a good sport about it to the bitter end.
I missed the takeoff.
He didn't miss the takeoff. The landing was off. All right, so it's got kinetic energy.
A
The kinetic energy goes into deforming the pole. So it's going to turn into the elastic potential energy of the pole. So which means that the energy is being stored within the pole. All right, the pole has got some kind of restoring force, which happens to be a conservative force. The amount of work that you do against the conservative force like gravity by lifting something up is going to become stored in that object. So what's happening is he's just bending it, he's storing energy in it, he's storing potential energy in it. So there's going to be a restoring force. So the restoring force is going to apply a force on him, and then he's going to get displaced along the direction of the restoring force, which means that that energy stored in the pole is going to get transferred to him, and that energy is going to become his gravitational
and pole
potential
vault.
energy.
They can be hard on the body.
So that's how it is done. So notice that there are two conservative forces at play there. One of them is gravity. The other one is the restoring force. So the amount of work done against the conservative force is the amount of energy that you store.
A career in pole vaulting can be
All right, so that initial kinetic energy now turns into its final gravitational.
hard on the body.
So faster you go, the more energy you can store in the pole.
A career in pole vaulting can be hard on the body.
So faster you go, the more energy you can store in the pole, which means that
A career in
more you can bend the pole, more you can bend the pole, the higher up you're going to be able to go. This guy is moving real fast, which means that this guy's going to have tremendous amount of kinetic energy, the second guy. And he's going to convert that kinetic energy into the elastic potential energy of the pole so that he can take that energy back in the form of height. Except the deformation was such that the pole ended up breaking. It's kind of weird. I didn't know up until I saw this that these poles were actually graded. I don't know how they do the grading because they can snap. At first, I thought this was Kmart quality, and hence the reason why Kmart went out of business. For whatever the reason, I thought that was the quality of the pole. It's not. Evidently, he's got the wrong pole for this sort of stuff, and then it just shattered to pieces. All right. One thing that you need to know, this is just side information. A lot of the pole vaulters tend to be extremely tall. All right, and because you're interested in the distance between the center of mass, this distance between the center of mass and the height. Taller you are, faster you go, the higher up you're going to be able to go. The second guy does not have the height advantage, so this is tricky. This guy has to go really, really fast. He needs to run really, really fast in order to actually make up the difference. And unfortunately, he didn't have the right pole for that sort of stuff. So these guys can also run pretty fast, but their advantage is the height. All right, so there's a bit of a discussion here. So the discussion that we're about to have is important because it's a test question, obviously. All right, so this final height that this guy has, the height that he's generating comes from his kinetic energy. So faster you go, the higher up you're going to be able to jump. All right, and for an Olympic athlete, evidently they can get up to 20 miles per hour. I'm very surprised that they can run that fast with a pole in their hands. But the heights that these people are clearing require them to go around 25 to 26 miles per hour. All right, so I'm talking about the world record holders, the ones that are potentially competing for the world record or the Olympic record. Those guys, for them to be able to clear that height, they need to be moving faster than they could run. So the question is, where is the extra energy coming from for them to be able to actually clear that height? So here's what I get on the test, and this is the reason why it's going to hurt, which is fine, guys. I want you to hurt. It's not a big deal. Learn from your mistakes. Learn from your mistakes because we got upgrades, we got the final test, this and that. It's okay to fail as long as you're learning from it. It's not like you fail a test and we move on. You fail a test. It's a learning experience, so you pay a little bit better attention next time. All right, so a lot of you guys on the test, and I'm just giving it to you right now, so it's a recording, so you can go back and check it. If this were a test question, you will say, "Oh, this person is getting energy from the pole," because you can store energy in the pole. Yeah, but the amount of energy that you're putting into the pole comes from your kinetic energy. I'm already telling you that this person does not have enough kinetic energy that he can convert into his potential energy, which means that if all that kinetic energy that this guy has, by the time it gets converted into his gravitational potential energy, he's not going to be able to clear this height. This height, he's not going to be able to clear it because he doesn't have enough speed. Olympic athletes, for example, if they can get up to 25, if they could get up to 20 miles per hour, for them to be able to clear the world record heights, they should be around 23, 24, or 25 miles per hour. They can't get up to that speed. Those are sprinter speeds. All right. Usain Bolt is around 23 miles per hour. There's no way you're going to be moving at 25 miles per hour with a pole in your hand. It's not going to happen. Yet these people clear those heights. So the question is, where does that extra energy come from? It does not come from the pole. All right. The pole has a restoring force in it. By bending the pole, you're doing work against the restoring force, which means that you're taking your kinetic energy and storing it in the pole and you're taking it back. It's like your bank account. You cannot put in more than what you can withdraw unless you're robbing the bank. You simply cannot do that. So you're not putting enough energy into the pole that you can take up, which is going to allow you to be able to break the world record. So you got to come up with an explanation as to where that extra energy is coming from. The short answer is it's coming from your muscles. All right. So you need to be well coordinated. You need to be extremely strong. And then the timing. All right. This guy obviously has got the proper height. He's able to generate a proper height, but his timing is a little bit off. All right. So the extra energy is going to come from the muscles. So the pole vaulting problem is one of the problems that I'm going to focus on because I kind of like this problem. It's a nice little test problem, usually. This is either an upgrade quality or college physics quality. For university physics students, this is way too easy. So, but if you're a university physics student, if you fail the math portion of the test, I recommend that you take a look at it because I can make this real interesting. So the initial form of energy is going to be all kinetic. Final form of energy is going to be all potential. In between, the kinetic energy turns into the deformation potential energy. Deformation potential energy is going to turn into the gravitational potential energy. So, which means that you can skip the intermediate step. Look at the initial form of energy, kinetic. Look at the final form of energy, it's going to be all potential. So you got the kinetic energy, you got the potential energy. Figure out the initial speed required to jump this height. And then you end up getting like 21.5 miles per hour. All right. There's no way anyone is going to run at 21.5 miles per hour to clear 15 feet. So the question is, where's the extra energy coming from? So it's going to be coming from the muscles. Also, there were some assumptions that went into the solution, which were kind of wrong. I put the center mass at the ground. All right. So in reality, you should look at the distance between the center of mass to the actual height, as opposed to the distance between the ground and the height. So which means that I have to put the initial height here somewhere for it to work. So that would be the approximate distance of where the center of mass is. Also, there was an assumption. So this initial height had to be about 3, 4, 5 feet, depending upon how tall the person is. And the other assumption, which was erroneous or wrong, was this person does not come to a stop. There's a horizontal speeding law. And then the person is going to land on the other hand, on the other side. All right, so I can make this problem rather interesting in such a way that I can give you the landing point of the person if you're a university physics student. So you would have to do a projectile motion calculation to figure out what the speed is. And from that, you can figure out the initial speed of the person for a given center of mass. All right, I can make it real interesting. There's a lot of room here. For university physics students, yeah, I could make it interesting. For college physics students, something like this is usually good enough. I would probably give this height of the center of mass and then let you repeat the same computation. All right, it's the asteroid impact. All right, so we got heat, we got light, we got sound, and then we end up getting a deformation crater. All right, so which means that through friction, energy is getting converted to heat, light, and sun, and deformation. So the question is, what is the initial form of energy that gets converted into other forms? A lot of you guys thinking that the initial form of energy is kinetic. It's not. This thing is moving. It's got kinetic energy. Also, the motion is happening under the influence of gravity, so which means that it's also got potential energy. So the initial form of energy is a combination of kinetic and potential energies. So the mechanical energy is the one that gets converted through friction to other forms of energy. Power is how fast the work is done, how fast the energy is transferred. So it's work over time. All right, so in the United States, we use horsepower. In physics, we use watts.
Makes up around 700, 720 horsepower. So that's probably, triple or better of what your passenger car Monte Carlo runs.
Racing teams carefully guard engine performance stats. But depending on settings, these cars can develop over 800 horsepower. This means 0 to 60 in 2.2 seconds, 0 to 100 in slightly over 4, top speed of blistering 240 miles per hour or more. Shelley drives a typical top-fueled dragster. If a vehicle generating 30 times the horsepower of a normal car can be called typical. To power this beast, a potent mixture of nitromethane and alcohol is used and makes it nearly a bomb on wheels.
Drag racing's great because the horsepower. My car has 6,000 horsepower. Average street car probably 200, less than 200 actually. This is 6,000. You sit in it and you're strapped in as tight as can be, and each car's built for the driver. The tighter the car, the safer the driver when I crash or when you crash.
All right, so the horsepower, what is it? What kind of information does it convey? All right, so the definition of it is straightforward. How fast the work is done, how fast the energy is transferred, how fast the energy is converted, how fast the chemical energy turns into kinetic energy, blah, blah, blah. Okay, but what does it convey from a vantage point of someone who's a non-physicist? It just means higher the horsepower is, faster you're going to get up to 60 miles per hour. So 0 to 60 within 5 seconds, 7 seconds, 10 seconds, 2 minutes, 5 minutes. That's what it means. All right, so how fast the chemical energy gets converted into speed, in essence. All right, how fast do you go from 0 to 60?
It makes up around.
All right, so higher the horsepower is, the sooner you're going to get up to 60 miles per hour. That's the way it is usually stated in the United States. So the power is how fast the work is done, how fast the energy is converted or transferred, how fast the energy is converted from one form to another. So how fast the work is done, work over time, how fast the work is done. That's what it means. All right, so work is a process of transferring energy. So how fast the energy is transferred. And also, work is a combination of force and displacement. So do back substitution, displacement over time is going to be velocity. So which means that the speed with which the force is going to get transferred. That's what it means. All right, so transfer of force, the speed at which the average force is being transferred is your power. So it's got a bunch of definitions. They all mean the same thing. So how fast the work is done, how fast the energy gets converted to kinetic energy in the case of a car, for example. So how fast you go from 0 to 60, that's what it means. How fast the energy gets converted to potential energy, like how fast you can lift something up. Also, how fast you can transfer force. It's a combination of speed, force, and speed. All right, so these W's and Omegas, just ignore those. They don't mean anything. When the Word files were converted into PDFs, all of a sudden they just appeared out of nowhere. So power is going to be expressed in terms of W. W means watts. In the United States, we use horsepower. So that's our conversion, and that's as far as we go. All right, now let's. All right, so let's go back and focus on a few problems.
Stand up.
The group is ready for the
All right, so we've been forever talking about these guys. So 78 miles per hour here, 91 miles per hour here. What if these people decided to jump directly from the bridge? All right, would they have been going faster or slower, about the same speed? All right, guys, those are test questions, obviously. All right, every single competition that we do, we're allowed to do more like it. Can be done with the assumption that the gravity is the only force acting. All right, so which means that the mechanical energy is going to be conserved, and which is going to allow us to be able to do certain computations. You can always figure out the final speed of anything that you want. All right, so that's how it is usually done. For example, after the cable snaps or the harness breaks or whatever, so we can figure out the final speed. The only thing we have to do is just look at the initial total energy and look at the final total mechanical energy. All right, and so initial and final mechanical energies will be the same. Mechanical energy is a combination of kinetic and potential energies. Initially, they're not moving, so the initial speed is 0. So initial kinetic energy goes to 0. Final height, I always measure it relative to the lowest point in motion, so that's going to be 0. So you do a little bit of a computation. You do your algebra, and then you come up with an expression, mathematical expression. This tells you that the final speed is always going to depend on the initial height, and then you plug the numbers in, and you get an expression like 91 miles per hour. That's it. So what if these people decided to jump from the bridge into the water down below? All right, would they have been going faster or slower, or about the same speed? A lot of you guys thought that they would be moving faster. The reality of it is gravity is the only force acting. The only thing that really matters is the initial height and the final height. That's it. Initial location and the final location. That's check to see what's happening in the initial location. Check to see what's happening in the final location. If gravity is the only force acting, you need to know what the initial speed is, and you need to know what the final height is. The initial speed is 0. The final height is 0. As a result, the computations will be exactly the same. So which means that if it's 91 miles per hour here, it's going to be 91 miles per hour there. So the path of motion is not going to matter. So this is a little bit longer. This is going to be a little bit shorter. And result is the same. You want to do sightseeing, this is the way to go. You're in a hurry, this is the way to go. The reason why everyone gets thrown off is because this motion is unimpeded and this motion is impeded by a cable. All right, so the question is, how come the cable is not transferring any energy to the system or taking away any energy from the system? All right, so now you have to use your understanding of what's going on. The cable experiences tension. All right, so the tension force is a reaction force. It's an induced force in the first place. All right, so this tension is always 90 degrees to motion. So which means that it doesn't really contribute to motion in terms of transferring energy. All right, so it's 90 degrees to motion at all times. So it's going to be 90 degrees to motion. When it's here, it's still going to be 90 degrees to motion because the motion is in this direction. So the tension force, the reaction force is always 90 degrees to motion because it's 90 degrees to motion. It does not transfer it does not transfer any energy to the motion. It doesn't add energy to the system. It does not take away energy from the system. The only thing it does, it really causes a delay in the motion. It introduces a delay in the motion. All right, so the tension force, aside from gravity, tension force is a reaction force to weight, to gravitational force. It's always 90 degrees to motion. So it does not add or take away energy from the system. Or It does not add any energy to the system. It does not take any energy away from the system. Okay, so problem number 1 and 2 for multiple choice, simple ones you need to know how to do. Just know how to use the formulas. 3 and 4, we had those for discussion purposes. Problem number 5, know how to do that from a perspective of multiple choice. These are way too easy for show work problems. Conservation of mechanical energy, 6, 7, 8. All right, all these problems are the same. Just pick and choose the one that you want to focus on. Make sure that you know how to do it inside out. Okay, this is 6, 7, and 8 for, these are for college physics students. These are fairly easy, straightforward problems. All right, so problem number 10, college physics, university physics, doesn't matter. Make sure that you know how to do it. We've done it in class. Look at the solutions. All right, so this stuff is important. That requires a restore. This is a restoring force problem. Question number 11 is the one that we looked at. So for college physics students, so just focus on that one. All right, question number 12. Okay, so question number 12 is university physics quality. All right, so this is the one that we will focus on. All right, so we'll take a look at that. We've done it in class. We'll go over it one more time. All right, you need to know how to do this sort of stuff inside out. Inside out. All right, make sure it's your, not only is it part of your muscle memory, you need to develop an understanding of it, that every single curve that I throw at you, you should be able to actually do this problem without even thinking. Just develop an understanding, guys. It's not, this is not just muscle memory. Algebra is muscle memory, but when you analyze something like that, you should be able to solve it for every single variable. This is for university physics students. This is good math. So 12 is the one that I want you to focus on for university physics students. And then I also want you to focus on 14. All right. 13, know how to do 13 for the college physics as well as university physics for the multiple choice. This is multiple choice quality. Question number 12 is a test quality for university physics student. 14 is a test quality problem for university physics students. 15 is just unbelievably adorable. I love this one. All right. In-person test, usually there's an extra credit component. And I would have these extra credit problems on the test. Extra credit is, it's extra credit, guys. If you got the skills, the talent, and everything else, you should be able to do it. If you don't have it, you don't have it. All right. Can you develop that kind of a talent and understanding? Talent is something that you're born with. You can only develop your skills. If you're lacking it, obviously you're lacking it. I don't know what it is that you can do to develop that sort of stuff. Okay, so this is one of the problems that I need you to focus on. Once again, it's a standard physics problem. A lot of the problems, short work problems, are standard physics problem. Of course, if you're Googling it, you're not going to be able to find it because the wording is mine. I use real life examples. It's not going to come up. But the solutions are standard solutions for problems like this. So you got this car. So we're looking for the power required for this car to climb up a 10-degree hill at a steady speed of 60 miles per hour, right? And assume that the retiring force, the frictional force, is 154 pounds throughout. So there's going to be a constant friction. The first thing you need to do is you need to literally draw things out. So this is going to represent the center mass of the car. All right, it's got weight, which is this value. It's sitting on a surface like that, so it's got normal force. All right, so the motion is in the opposite direction, so there's a constant friction opposing the motion. I'll call D. I think the drive force is probably adequate. Then what I'm going to do is I'm going to set up my coordinate system, X and Y coordinate system. And everything that I'm doing here, the solution is going to come out of this. All right, so I want you to practice stuff so you're comfortable with algebra. When you guys do math, I don't want you to go, oh, let me look this up, let me look that up. I don't want you to do that. When you're reading a book, you don't look up the alphabet. All right, make sure that it's part of your muscle memory. Make sure that you can do this. Whenever you're writing something, you don't look up the alphabet. It's muscle memory, guys. You just write things along. The math is the same way if you're an engineering or physics student. The math is not something that you should be thinking about. All right, you're not a mathematician. Don't worry about the theories. Just know how to do the practical stuff, like the algebra. And in more advanced courses, the calc is going to be second nature. Even more advanced courses, differential equations is going to be second nature. Don't worry about how the mathematicians come up with the rules. Just know the rules. Enough. In fact, don't even worry about knowing the rules. Make sure that your muscles know what the rules are. All right, just let it go. Just let it go. And for you to be able to solve a physics problem, if it's a force problem, you need to show where the forces are. And the forces, if they are applied to the center of mass, make sure that you got a center of mass. All right, so everything that we're about to do is going to be related to this. Notice that this angle is the same as that angle. Just make sure you know how to move these angles around into the XYZ coordinate system. This is friction, is opposing motion, which means that the motion is in the opposite direction, if that's the case. So what is the amount of power? What is the power required for this car to climb up a hill at a constant speed? All right, so I'm doing my conversions. Obviously, this is mass. I'm going to express it in terms of kilograms. So speed is going to be expressed in terms of meters per second. I'm saying it's constant, so that's important. Why is it important? You will find out. Because these are initial conditions. Just state the facts. Don't put in more than one single question mark. Because whenever I'm grading, if there's one single question you need to answer, make sure that you put in the facts, not your assumptions. Okay? Because I don't want you to clutter it. Your assumptions don't belong in here. Just facts, the facts, only facts. This is it. Here's your unknown. These are what's given, and these are the converted numbers. And that's it. That's it. Whatever you do, make sure that you understand that solution should be geared towards what you can measure, what's given to you. All right, so the next step is the power equation. The power equation is powerful. Oh my God. It's either how fast the work is done, how fast the kinetic energy is transferred, how fast the potential energy is transferred, blah, blah, blah. It just goes on and on and on. So I'm just going to pick only the portion of it which is related to force and related to speed. Okay, why? Because the speed is given. Why the force? Because all of a sudden their force is more. All right, so I'm thinking, that's probably the best thing to use under the circumstances. All right, so what force is responsible for this motion that I'm looking at? I say, oh, okay, so it's the drive force is going to be responsible for it. Now you have to pick and choose because this is a generic expression for force. All right, so the power is generated by this force itself. All right, so which means that I need to figure out what this D is going to be. So drive force is the force responsible for the power. All right, so the next question is, I'm looking at this, I say, yeah, but the D is not given. So does this mean that we're going to go to hell? The answer to that question is yes. We're about to step into hell right now, because which means that we will have to attempt to solve this problem. So we need to come up with an expression for D. So you got a bunch of forces. So I noticed that the D is a force on the x direction. So why not just sum up the forces on the x direction? All right, so D is in the forward direction. Lowercase f is pointing in the opposite direction. And then along the x direction, the weight is going to have a contribution. So the weight has a component along the x direction, pointing to the left. So you got your small triangle. So it's going to be opposite over the hypotenuse. So opposite over the hypotenuse is going to be your sine. So it's going to be W or mg times sine of the angle. And then you sum up the net force, and the net force is going to give you the acceleration on the x direction. But I know that this thing is going up at a constant speed, meaning that the net force on the x direction is going to be 0. All right, and so that's the expression that we got. So now we can just isolate D from here. All right, so this expression is going to go back into that one. All right, so the question is, do we have numbers for everything? Do we know what the frictional force is? Do we know what the mass is? Do we know what the angle is? Do we know what the speed is? So answer to those questions is yes. So you know what the frictional force is. You know what M is, you know what J is, you know what the angle is. So it'll give you an answer in terms of watts. And then the next thing we need to do is just express it in terms of horsepower. So the horsepower is going to be 110 horsepower. All right, this is for university physics students. This is an elegant solution. I kind of like it. It's not that complicated. If you know what you're doing, you can do it within 10 minutes or less. But a lot of once again, the work is done algebraically. You get to use the calculator once after you do your conversions initially. At the end, okay, no numbers in the middle. As soon as you use a number, you will lose points. All right, so you get to do one single computation at the end after you're done with the problem, and then you do your numbers, come up with a number in terms of standard units, and then convert it to the units that you can understand. The horsepower is something that you understand, and that's it. Okay, so problem number 12. This is what I was looking for. It just came out. I was about to do this. Question number 12. Okay, so this is the next one. This one is once again, these are standard problems. So accident scene investigation. We've done a problem like this before by using the net force. We did a problem like this in the applications of Newton's laws task. All right, so now we will get to do it using the conservation of total energy or work-energy theorem. That's what we will get to do. All right, so what do we know? The car is going to skid to a stop. All right, so you measure the skid marks. And somehow the estimated coefficient of kinetic friction is 0.42. So figure out the speed of the car when the driver slammed on the brakes. Okay, so that's what we need. All right, so skid marks measure 233 feet. So the length of the skid marks, coefficient of kinetic friction, initial speed of the car. All right, so we'll do the conversions and we're done. Okay, so let me just stop at this point. Okay, so this is probably the 10th time I'm saying it, if not the 20th time. I'm just going to keep saying it until even the last person gets it, because we're halfway through the semester. I'm still seeing the same problem in the solutions. List everything here, do your conversions, and then don't touch the calculator until you're done. All right. Your looking for one thing and one thing only. I don't ask for 10 different things. Just find what it is that you're looking for, put a question mark next to it. This is your target. So if you get confused, you can, instead of gazing on Facebook or a computer or TV, you can just gaze at the question mark, check to see what it is that you're going after. So if you get confused, this is what you need to be looking at. This is your target. This is what you're trying to isolate. Put a question mark next to it, put the proper unit next to it, and put the converted unit next to it. Whatever it is, you want to be able to express it in the form that you understand it. Draw your force diagram. Just visualize it. All right. Make sure anything and everything related to your solution is already here. These are your listings and the conversions. These are your initial conditions. Make sure you got the proper symbols. If you're going to introduce a symbol, all of a sudden something completely new that no one has seen before, make sure you explain what it is it represents and why you're using that symbol as opposed to using a traditional symbol. Because make sure you explain and justify why you all of a sudden decided that you're going to use something real bizarre. All right, or else it's not acceptable. Okay, don't do that. Just agreed upon symbols are the ones that we get to use. I will probably go, okay, so this guy really cannot draw mu because he doesn't like Greek. Okay, I'll say, okay, so you like Chinese alphabet? Make sure that it's explained. All right, because you got some kind of phobia or something against Greek letters. Explain it. You say your doctor said, hey, it just, for whatever the reason, it's got an adverse effect on your medication or something. Just come up with some kind of a really decent, understandable explanation if you're not going to be using the symbols that we're using. What I'm saying is don't use anything else. That's the bottom line. Just use the symbols so that you don't have to explain yourself. And then the next thing is, on this test, your solution has to be related to the topic of the test, which is work-energy theorem, the conservation of energy, conservation of mechanical energy. So you cannot use concepts or formulas related to any other chapter in the future or any other chapter previously. All right. So if I say, hey, this is what I want you to use, this is what you use. So there are two ways of solving it. One way of solving it is using literally Newton's laws. The second way of solving it is literally use the work-energy theorem, and that's what we will get to do. So this is what we will get to use. So we will end up using the work-energy theorem. So the work is the same as the amount of energy which is transferred. So the work is a process of transferring energy, and in this case, the energy is going to be transferred in the form of kinetic energy. That's it. So I'm just looking at it. I say, okay, so these are the things that I can use, and that's what I'm going to do. All right. So work is a process of transferring energy. So what's happening is the energy is being transferred in or out of the system in the form of kinetic energy. So what's happening is the system is losing kinetic energy in essence. Okay, so very good. All right, so from that, I can figure out the initial speed. All right, so at this point, I'll stop. Let's check to see what else we could do. Mass of the vehicle is not given. And sometimes I get an email from someone, you just forgot to give us the mass. No, I didn't. It's not needed. If you want a mass, just use your own car's mass. I don't care. It's not going to make any difference. All right, so the next question is this W, the work. So what is work? All right, now we got to go to the definition of work. The generic definition of work is force causing displacement. All right, and the question is, what is the force which is responsible for that displacement? The force responsible or affecting displacement is the frictional force, which is opposing motion. All right, so I'm just going to do a back substitution there. All right, so negative times negative is going to be positive. All right, and they didn't give us an expression for the frictional force. They gave us an expression for the coefficient of kinetic friction. So, but we know what the expression for the frictional force is. So it's going to be mu sub k times n. N is not given to us. So now we have to come up with an expression for n. So n is a force along the y direction. It's a reaction force to the weight in this case. So don't assume that n is the same as weight. Okay, in the previous problem that we were looking at, it wasn't, because the car was at an angle. The car was on an incline. So don't make assumptions. Just let mathematics take care of it for you. So take a look at the net force on the y direction. N is up, W is down. Net force on the y direction is going to be 0 because the acceleration is 0. So which means that N is the same as W. You can do a back substitution here. And now we came up with an expression for the frictional force. Do a back substitution here. And notice that the masses will cancel, so the mass doesn't matter at the end. Okay, so we came up with one single final expression, and then at this point we will stop and look at the numbers. Do we have a number for mu sub k? Yes, we do. Do we have a number for g? Of course we do. Do we have a number for the length, the distance that the car skids? Of course we do. We're done. All right, so now you can plug the numbers in just once, and then meters per second. Of course, it's not the unit that we're interested in because we cannot relate to numbers in terms of meters per second. Let me share a secret with you guys. No one can relate to numbers in terms of meters per second. I don't care where you're from. All right, you guys, those of you guys who were born and raised in the United States, you're thinking, oh, so I bet the people who were brought up in different countries that use the metric units probably understand these numbers better. Absolutely not. All right, when you express numbers in terms of meters per second, no one gets those numbers. All right, because we express speed in terms of kilometers per hour. Our kilometers per hour, people can relate to. Meters per second, no one can relate to. Just like in the United States, miles per hour, everyone relates to. Feet per second, forget it. I don't even know why people, it's just the weird nerds. Sometimes some physicists just throw those numbers around as if it makes sense to other people. It doesn't. Sometimes engineers just use it. It's like, get a life. All right. Just, if you're not going to be able to express numbers in terms of people, in terms of something that people can understand, don't waste your breath. Don't do that. All right. 24.19 meters per second does not make any sense to anyone. If you're a European or outside of the United States, kilometers per hour, it makes sense. Meters per second doesn't make sense to anyone. All right. So, which means in the United States, you convert it to miles per hour. Outside of the United States, kilometers per hour. That's it. So give it back to people in the way these people can understand and relate to. So 24.19 meters per second is 55 miles per hour. Now there's no debate. You go, okay, so the car was going at a reasonable speed, depending upon what reasonable is, depending upon the speed zone. That's it. So skid marks indicate that the car is moving that fast. All right, so guys, practice this. Not on the day of the test. You need to start practicing it. Give yourself enough time for your brain to go, okay, now this starts to make sense. All right, absolutely don't practice it during the test. Don't do that sort of stuff. It's the purpose of the test is to force you to review stuff. And hopefully, I don't know, 6-7 tests into it, I want you to take a look at your performance and then start making adjustments for it. All right, which means that either you're not preparing on time, or you're not giving yourself enough time, or you're not studying enough. And the conceptual sections of the test, I got to tell you, the conceptual sections, every single question is discussed in the lecture. What I'm looking for is a summary statement, explanation, and justification. And the best way to study for this, all right, find someone who does not really understand. Find someone, maybe a child, someone who's really slow, who doesn't have a great grasp of reality, and try your best to explain it to that person until you see the lights in their eyes. All right, explain, explain, explain. You have to force yourself to explain everything. Explain and then justify. Explain and justify. Move on to the next person. Move on to the next person. I'm not kidding. I'm not kidding. Because unless you can explain it to someone who does not understand this concept, unless you can explain it to someone who's not going to agree with you, all right, you're not ready for these tests. Okay, because I heard from someone, oh, you're not giving us enough time. Are you kidding? 5 minutes for something that you already know, that's plenty of time. That's plenty of time. I'm testing your preparation. I'm not giving you a question that you've never seen before. By the time it's a test question, it's been discussed inside out, at least once, if not twice, if not 3 times. All right, just focus on that stuff. That's how you get ready for these tests. I know you guys have to work. Most of you guys have to work. I get it. Also know that you're taking other classes. All right, it's time management. It's time management. Okay, physics is hard. It is probably the hardest course that you're taking right now, and possibly the hardest course you will ever take. And the physics is probably next to math. This is the most useful course that you're taking in terms of your careers. When I say next to math, obviously math is assumed that you can do math. The physics is the most important course that you guys are taking right now. All right, because the math, you really don't need to understand the concepts to the same degree, but physics you do. All right, so this is pretty much it. I think I went over the concepts. Okay, the derivation is not that important. And that's pretty much it. So those of you guys who want to stick around, if you have any questions or whatnot. All right, so let's go over your questions. The conceptual portions of the test number 6 and 7 are graded. Okay, I just did the video editing. I'll put the stuff online. All right, and then I make the grading available. So I want you guys to check to see how the grading is done. If you have any questions, just ask. I'll be more than happy to go over your answers with you. So that's not a problem. I just want to make sure that we do it in an organized sort of fashion so we're not wasting a lot of time.